And here's a planning problem. Here's how we compute the price. So the planning problem, so we're going to flip that problem, flip the equilibrium problem into one big planning problem. The way we think about it is kind of think about Pareto program. We maximize expected utility of the agent subject to all constraints. First three constraints is like what the agent can do in terms of X. Okay, this is a consumption possibility set. And then we make sure that whatever X that we choose from this planet has to be true that output has to be bigger than consumption on average. Okay, or the same at least. And this Lagrange multiplier of this will give me the price of the contracts. Okay, there's some formula that you can derive. But that's how we solve this linear programming problem. Instead of solving the equilibrium directly, we solve a big planning problem, which is one big optimization problem, maximize expected utility subject to all constraints. And there's no prices here, right? So that's the key, that because we assume they cannot retrade, and this is like the usual planning problem. There's no prices. Is that okay? And, oops, sorry. Yeah, just before I start with this slide, Prescott-Townsend showed that the planning problem is kind of the same as equilibrium. Okay, that's the key result. They are efficient. There's going to be price that give us exactly what solved that big problem. So the market should work fine. So that's the idea. But now let's start talking about retrading. Okay? So what's retrading here means? Retrading here is going to be right after you execute a contract. Suppose you take a contract A, C, and Q. Okay? Your output is Q. Now you get C. You already take action A. Given that, now you're going to decide if you like the C or not. You may not like it. You can go to the market and say, I want to buy tau 1 unit of C1, of good 1, and tau 2 unit of good 2. In such a way that the total value of what you're going to buy is equal to 0. So which means actually you buy and sell, right? You buy good 1, you sell good 2, or vice versa. Given the price though, okay? You can go to the spot market. That suppose that the spot market has a price P of Z. I'm going to use C later. That's why I put C here. So the P of C I'm going to call it spot price. It's a price that clears the spot market. Here, let's assume that everybody can enter to this spot market. P of C is a price such that given that price, everybody choose tau 1 and tau 2, right? In such a way that tau 1, the aggregate of tau 1 equal to 0, and the aggregate of tau 2 equal to 0.
Why do I want to go back to the spot market after?
Oh, okay. You're going to... Okay, I can tell you now, I'll show you example later. Because in Prescott-Townsend, the optimal allocation that you're going to get from Prescott-Townsend, in some case, the agent will have different marginal rate of substitution. Remember, sometimes Prescott-Townsend will tell you do this. So this is agent 1, this is agent 2. And we know that if you're here, everybody better off going here, expose, right? It seems easy, but it's not, because if you move there, you kind of change incentive constraint. That's the problem. Here you have tension between X and expose. Expose people want to move because their marginal rate of substitution or slope in different curve are different. Okay? So because they know that they can do better by trading with each other. They have willingness to trade. Is that okay? And that because Prescott-Townsend solution sometimes prefer this point instead of the point that they are tangent. Okay, and we show you when this happened. If this happened, then there's no problem. Okay, and it's good point. And given that they can do this, when you decide contract, you have to take that into account. Okay, and first I'm gonna call this C as market fundamental, just to make sure that it's not really necessary. You can think about C as a spot market price, no problem. But some people may say, oh, planning problem never have price in there. Okay, we just want to make sure that actually when in the planning problem, this is not really a price, this is a function of C. Okay, you should look at this as a function of C. And once you allow them to trade, IC constraint will look like that. It's a bit different, right? Instead of utility, now it's indirect utility. So here it tells you, oh, suppose you get C and A and Z, then you can retrade what you get. Here we need to allow them to retrade. Okay, when we decide contract, we allow them to retrade. When they deviate, they can retrade too. Okay, so that's already different. And that's going to make a big difference. Okay, and And then also, as I just said, to make it consistent, the P of C has to be the market clearing price in such a way that the tau that people choose from here, everybody that choose tau, I mean from everybody, you sum everybody, has to be aggregate out to 0. Okay, that means someone has to buy, someone has to sell good one, and vice versa for good two. Is that okay? And we call this insistency constraint. Is that okay? So we don't want to be crazy and say, oh, there's a price and the price never really show up. This constraint makes sure that this price really is a spot market price. Okay, it's a price that really happened. And just before we move on, I'm not going to tell you the proof here, but you can imagine that here, since we allow any type of contract is possible, actually we can rewrite every contract we want in such a way that the consumption that we're going to give to the agent given the price C is going to be such that the consumption is exactly people don't want to trade. Okay, it's just without loss of generality. When we put in computer, then it's easier. We don't have to have many grids. Okay, we kind of have some constraint on the grids. And also, this is going to make it look closer to what Prescott-Townsend has. You can see that on the left-hand side, it's exactly the same, right? When we constrain that grid, the left-hand side is like, oh, okay, you get utility from C because you don't trade. You consume exactly like that. But on the right-hand side cannot be the same because once you take different action, right? Even C is kind of solve the utility maximization that I just showed you before at A. But it doesn't have to solve the same problem at A problem. Okay? So that's the key. So once you deviate, this C is not like utility maximization C anymore. You may want to retrade. Okay? And that's the problem. Everything else looks the same though. And then using the proof of this one, we can also show that actually once we constrain C to be without trading, the consistency constraint that I just showed you will just hold every time. So we don't have to keep track of that. Okay? Because we instead constrain the grid on C instead. Is that okay? So that's why I'm not going to talk about constraint C anymore. But it's there. I mean, we have to have it there because otherwise the price may not be what we just talked about. You have to make sure that the price is the right one.